Let's turn our attention to circuits, defined as the path of conducting material between two terminals that charges can follow. So here I'll give you an example of a circuit diagram. I have here a battery. On this side I have some negative charge. On this side I have some positive charge. This is a switch. And over here, let's say that I have some light bulb. Okay, for electric charge to flow here, the path must be complete, meaning I need to turn this switch so that these wires are all connecting so that my electrons can flow to this positive terminal like they want to go towards. Notice that this is creating the electron flow. We have electrons that want to move from this side and get to the positive side. So our battery creates what I'll say is pressure, though we know it's electric potential that makes electrons flow. And secondly, I'll say about the battery, it's a chem reaction in which positive particles are moved up to this positive side. Even though it's already positive, there's a chemical reaction doing work, pushing the particles up here, creating this voltage. So carry positive charges to the positive terminal. That is work done. So the flow only happens when switch is closed. And just about the conventional way of drawing current, we would say in this diagram that when the switch is closed, current is going in that direction. But we know it's electrons that are moving, so the electron flow is really going that direction. But that doesn't really have a place on our circuit diagram. This leads to Ohm's law. Ohm's law. What's happening here? So some materials allow charge to flow better than others. So most of your wires will be copper. So another way of saying that some materials allow charge to flow better than others is to say that materials will differ in the way they resist current. If instead I take out this copper wire and I have a sheet of glass, then they will both differ in the way that they resist current moving through them. And we're going to try and come up with a few expressions, or one expression based on a couple relationships. But my final note here is that this could be called resistance. The way that a material resists current will be called resistance, and we'll measure this in ohms. Okay, and I'll call this R. So what would happen if I have a greater resistance? Higher resistance, it's going up. What happens to I? Well, the current must go down, right? If you have more resistance, then there's less flow. So lower current. How could I express this? Resistance must be proportional to the inverse of current. If resistance goes up, then current goes down. Or I could say same thing, just placed in that form. So if resistance goes up, current goes down. What else happens if, let's say, I increase the voltage? So higher voltage, think pressure, what happens to the current? Well, there must be a higher current. So relating those two variables, I could say that voltage is proportional to current. Now I want to tie these two together into one beautiful equation relating I, V, and R. Well, I is proportional to V, so V must be on the numerator, and R should be on the denominator. And that is Ohm's law, that the current is the voltage over resistance. Current, voltage, and this is resistance. Where the voltage is the pressure on charges. Okay, that's Ohm's law. We will explore in future videos how to apply this. See you then.